A jet stream is tearing across the equator of Jupiter right now, moving at 320 miles per hour, hidden above the cloud tops where no human eye and no previous telescope had ever been able to see it. It took the James Webb Space Telescope, a machine built primarily to look at galaxies born more than 13 billion years ago, to find a river of wind racing around a planet sitting in our own cosmic backyard. That single fact tells you almost everything about why Webb's images of Jupiter matter, and why they deserve a serious look instead of another round of clickbait headlines promising mysteries that scientists supposedly cannot explain. The real story here does not need exaggeration. It is already strange enough, already beautiful enough, and already important enough on its own terms. Jupiter is the largest planet in the solar system, more than 11 times the diameter of Earth, and it has been photographed by dozens of missions since the Pioneer and Voyager spacecraft first flew past it in the 1970s. Cassini, Galileo, Juno, and the Hubble Space Telescope have all produced iconic images of its swirling bands and its famous Great Red Spot, a storm wider than Earth itself that has been raging for at least a century and a half. So when the James Webb Space Telescope turned its enormous 6.5-meter gold-coated mirror toward Jupiter in July of 2022, only weeks after its very first science images were unveiled to the public, the obvious question was simple. What could an infrared observatory designed to peer at the faintest and most distant galaxies possibly add to a planet we had already been photographing for half a century? The answer, it turned out, was a great deal. Webb does not see Jupiter the way our eyes do, and it does not see Jupiter the way Hubble does either. Hubble captures visible light, the same wavelengths our eyes process, which is why its Jupiter images look like postcards, rich in orange, cream, and reddish-brown bands. Webb's primary instrument for planetary imaging, the near-infrared camera known as NIRCam, captures wavelengths of light invisible to the human eye, light that reveals information about altitude, temperature, and chemistry that visible light simply cannot carry. When astronomers process a NIRCam image of Jupiter and translate its infrared data into a color palette, we can perceive something remarkable happens. The atmosphere stops looking like a flat painting and starts looking like a three-dimensional structure, with towering storm clouds glowing brightly against darker, lower haze layers, and the usually crimson Great Red Spot rendered in stark white. Because at these wavelengths, brightness corresponds to cloud top altitude rather than the reddish chemistry that gives the storm its name in visible light. That first batch of Webb images from the summer of 2022, produced by planetary astronomers Imke de Pater and Thierry Fouché, along with citizen scientist Judy Schmidt, showed far more than the Great Red Spot. They captured Jupiter's faint ring system, ordinarily far too dim to notice next to the planet's overwhelming glare, along with two of its smaller moons, Amalthea and Adrastea, appearing as tiny points of light near the rings. The same set of images caught the moon Europa sitting to one side of the Great Red Spot, its shadow cast directly onto Jupiter's cloud tops below, a small dark dot marking an eclipse in miniature happening 500 million miles from Earth. Scientists at the Space Telescope Science Institute in Baltimore, including Brian Holler, who helped plan the observation, pointed out at the time that the achievement was not simply capturing another pretty picture of Jupiter. It demonstrated that the same telescope built to detect the faintest, most ancient galaxies at the edge of the observable universe could, in the very same mission, resolve exquisite detail on a planet bright enough to see with the naked eye from your own backyard. Few instruments in the history of astronomy have been asked to operate across such an enormous range of brightness and distance, and Webb did it in its opening weeks of operation. The infrared images also revealed something that visible light photography routinely misses entirely: Jupiter's auroras. On Earth, auroras form when charged particles from the sun interact with our planet's magnetic field and atmosphere, producing the shimmering green and red curtains of light familiar to anyone who has traveled to high latitudes to see them. Jupiter has auroras too, but they are far more intense and far more complicated because Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, the strongest of any planet in the solar system. Webb's infrared vision lets scientists see these polar auroras glowing brightly at both the north and south poles of the planet, and in the more recent, more processed composite images released in early 2026, that aurora appears vividly at the poles, layered on top of the planet's cloud structure and dust ring, forming one of the most information-dense single images ever taken of Jupiter. What makes Jupiter's auroras scientifically fascinating is not simply that they exist, but where some of their energy comes from. Unlike Earth, where auroras are driven almost entirely by the solar wind, a portion of Jupiter's aurora is fed by one of its own moons, Io, the most volcanically active body in the entire solar system. Io is squeezed and stretched by the immense gravitational tug of Jupiter and the gravitational pull of neighboring moons, a process called tidal heating, And that stress melts rock beneath its surface and drives constant volcanic eruptions that spew sulfur and other material into space. Some of that ejected material becomes ionized, charged, and gets captured by Jupiter's colossal magnetic field, which then funnels the particles along magnetic field lines down into the planet's upper atmosphere near the poles. When those particles slam into the atmosphere, they create a distinct glowing footprint within the aurora. Essentially, a visible signature of a moon's volcanic activity being drawn like a wire hundreds of thousands of miles long and burned directly into the poles of its parent planet. Webb's most detailed infrared composite images of Jupiter show this Io footprint clearly within the southern aurora, a phenomenon that is not a mystery at all, but rather one of the more elegant, fully explained examples of how moons and planets interact electromagnetically anywhere in the solar system. There is another visual feature in these images that regularly gets misread online as something unexplained or anomalous, and it is worth addressing directly, because understanding it actually deepens appreciation for what Webb is doing rather than diminishing it. In several of the sharpest Jupiter images, bright points of light appear to have thin, needle-like streaks radiating outward from them. Those streaks are not evidence of some strange energy phenomenon in Jupiter's atmosphere. They are diffraction spikes, an optical artifact produced by the physical structure of the telescope itself. Webb's 18 hexagonal mirror segments are held in place by support struts, and when extremely bright light passes through and around those struts, it diffracts, bending slightly and producing the 6 pointed spike pattern you see radiating from bright stars, and in Jupiter's case, from especially luminous cloud features or moons within the frame. Every JWST image with a very bright object contains this effect. It is simply physics interacting with hardware. The same way a camera lens can produce lens flare in bright sunlight, and professional image processors and NASA's own documentation account for it openly rather than treating it as some kind of scientific puzzle. The jet stream discovery deserves its own extended explanation because it is arguably the single most important genuine scientific finding to come out of Webb's Jupiter observations so far, and it rarely gets the attention it deserves next to flashier images. Researchers analyzing Webb data found a narrow, fast-moving jet stream sitting directly above Jupiter's equator, positioned above the main visible cloud decks at an altitude of roughly 25 miles, in a layer of the atmosphere between about 12 and 21 miles above the cloud tops, where Webb's near-infrared camera is particularly sensitive at a wavelength around 2.12 microns. This jet moves at roughly 320 miles per hour, an extraordinary wind speed, more than double the strength of the most powerful hurricane-force winds ever recorded on Earth. What makes the discovery significant is not just the speed, but the fact that nobody had detected this particular current before, despite decades of prior observation by other spacecraft and telescopes, because it sits in a very specific, narrow altitude band that earlier instruments were not equipped to resolve with this level of precision. Researchers were able to track it by comparing images taken several hours apart and measuring how cloud features drifted, essentially timing the wind the same way a meteorologist tracks a jet stream on Earth using satellite imagery, except this jet stream sits on a planet 365 million miles further from the Sun than Earth does at closest approach. Understanding Jupiter's atmospheric dynamics has real scientific value beyond simple curiosity. Jupiter is often described by planetary scientists as a natural laboratory for atmospheric physics because it is a gas giant with a churning, banded atmosphere that in some ways resembles Earth's own circulation patterns, just on a vastly larger and more extreme scale without the complications of oceans, continents, or a solid surface interfering with the fluid dynamics. Lessons learned from tracking wind speeds, storm behavior, and vertical cloud structure on Jupiter feed directly into models of atmospheric behavior on other giant planets, including the thousands of gas giant exoplanets discovered orbiting distant stars, planets far too far away to ever image with this kind of detail directly. In that sense, every improvement in our understanding of Jupiter's weather is also indirectly an improvement in our understanding of an entire category of worlds scattered across the galaxy. The most recent and most widely circulated Jupiter image from Webb, the one many people online mistakenly associate with claims of shocking, unexplained phenomena, is actually a carefully processed composite combining multiple exposures from the original 2022 NARICAM dataset, refined by planetary scientist Ricardo Hueso and image processor Judy Schmidt, and later featured by NASA's Astronomy Picture of the Day service in January of 2026. This composite is dense with real, documented, entirely explainable detail. It shows the difference between high-altitude, brightly reflective cloud tops and darker, lower-lying haze layers, with the Great Red Spot rendered as one of the brightest features in the frame precisely because storm clouds there are punching up to unusually high altitudes. It shows the faint ring of dust that circles Jupiter, invisible in most amateur photography because it requires long exposure and careful contrast processing to detect against the planet's glare. It shows two small inner moons, Amalthea and Adrastea, as tiny points near that ring, and it shows both polar auroras glowing at once, including the Io volcanic footprint described earlier. Every one of these features has a documented physical explanation rooted in atmospheric science, orbital mechanics, or electromagnetism. None of them represents an anomaly that has left scientists baffled, and any script, article, or video claiming otherwise is not describing real Webb data. It is manufacturing drama that the actual observations do not support. It is also worth directly confronting a piece of misinformation that has repeatedly circulated online under the banner of dramatic New Jupiter photography, because separating it from genuine Webb data matters for anyone trying to present this topic honestly. In the spring of 2026, a viral social media post claimed that NASA had released a stunning new image of Jupiter captured by the James Webb Space Telescope, describing it as coming from the most powerful telescope ever built. The image spread quickly, racking up tens of thousands of interactions. It was not, in fact, a Webb image at all. It was an art piece created by astrophotographer Andrew McCarthy, assembled from his own ground-based photographs and digitally enhanced for visual impact, never claimed by McCarthy himself to be a genuine Webb product. Community fact-checking on the platform. Mistake, and linking back to NASA's actual archive of verified Webb Jupiter imagery. This episode is a useful case study in exactly the kind of confusion that fuels sensational, inaccurate headlines about Jupiter and Webb. When a story about supposedly shocking or unexplainable space images goes viral, there is a real chance the image in question was never produced by the instrument being credited in the first place, and any serious presentation of this topic has an obligation to draw that distinction clearly rather than blur it for extra engagement. Stepping back to view the bigger picture, it helps to remember what the James Webb Space Telescope actually is and why it was built in the first place, because that context explains why its Jupiter images carry so much scientific weight, despite the planet being, cosmically speaking, right next door. Webb, launched on Christmas Day of 2021 aboard an Ariane 5 rocket from French Guiana, and after a month-long journey unfolding its mirror segments and sunshield along the way, it arrived at the second Lagrange point, a gravitationally stable location roughly 1 million miles from Earth, positioned so that the Earth, the Moon, and the Sun all stay on one side of the telescope, allowing its enormous 5-layer sunshield to keep its instruments in permanent, deep shadow. That shadow is essential because Webb observes primarily in infrared light, and infrared astronomy requires instruments to be kept extraordinarily cold, often below negative 300 degrees Fahrenheit, so that the telescope's own heat does not overwhelm the faint infrared signals it is trying to detect from across the universe. Its 18 hexagonal beryllium mirror segments, coated in a microscopically thin layer of gold to optimize infrared reflectivity, combine to form a light-collecting surface more than 6 times larger than Hubble's single mirror, giving Webb the light-gathering power to detect the dim glow of galaxies formed within the first few hundred million years after the Big Bang. None of that design was built with Jupiter in mind. Webb's headline scientific goals, as described by NASA, the European Space Agency, and the Canadian Space Agency at launch, centered on tracing the earliest galaxies in the universe, studying how stars and planetary systems form within clouds of gas and dust, and probing the atmospheres of exoplanets for potential signs of habitability. Solar system science, including observations of planets and moons within our own neighborhood, was included in the mission's plans, but it was never the primary justification for the telescope's multi-billion-dollar cost or its decades-long development timeline. That is precisely what makes the Jupiter results so compelling from a scientific, storytelling perspective. An instrument engineered for cosmology and exoplanet atmospheres turned out to be extraordinarily capable at planetary science within our own backyard, almost as a byproduct of its extreme sensitivity and resolution, discovering a jet stream that decades of dedicated planetary missions had missed entirely. It is worth pointing out how this fits into the wider arc of Webb's post-launch operations, because Jupiter has not been a one-time target. Since those first 2022 images, the telescope has continued gathering solar system data as part of its ongoing science program, including further studies of Jupiter's atmosphere, its moons, and its magnetosphere, alongside high-profile observations of other planets in our solar system. In early 2026, astronomers released a striking new infrared image of Uranus, produced after a study that mapped the vertical structure of that planet's upper atmosphere for the first time, showing that Webb's usefulness for solar system atmospheric science extends well beyond Jupiter alone. Around the same period, researchers used Webb to study a Jupiter-sized exoplanet named WD 1856b, watching it transit in front of its host star, a white dwarf, and using that transit to measure the planet's mass, temperature, and atmospheric composition. That particular exoplanet observation carries an almost poetic resonance, because the exoplanet orbits a white dwarf, the dense stellar remnant left behind after a sun-like star dies. Astronomers describe the findings as offering a preview of what could eventually happen to a planet like Jupiter itself, billions of years from now, after our own sun exhausts its fuel and collapses into a white dwarf of its own. In a very real sense, Webb's Jupiter-adjacent research spans not just the present state of our solar system, but a plausible glimpse of its distant future. Separately, other research teams using Webb have pushed the study of Jupiter-like planets even further outward, examining so-called cold Jupiters, giant planets orbiting far enough from their stars that their atmospheres remain frigid rather than scorched, unlike the majority of giant exoplanets discovered so far, which tend to orbit close to their stars and reach blistering temperatures. Lead researcher Elizabeth Matthews of the Max Planck Institute for Astronomy described Webb as finally allowing astronomers to study solar system analog planets in real detail, explaining that if intelligent observers many light years away were looking back at our own sun with an instrument as capable as Webb, it would be the first telescope powerful enough to study a planet like Jupiter in real detail from that kind of distance, even though studying a planet as small as Earth would still require considerably more advanced technology than what exists today. That framing captures something important about where we currently stand in the search for other worlds. Jupiter-sized planets, whether in our own solar system or orbiting other stars, sit right at the edge of what our very best current instruments can resolve in fine detail, while Earth-sized planets remain just beyond that frontier, waiting for the next generation of telescopes. All of this adds up to a picture of Jupiter that is scientifically rich without needing a single exaggerated claim. The planet's Great Red Spot, technically a persistent anticyclonic storm, appears bright white in Webb's infrared images because its cloud tops rise to unusually high altitudes compared to the surrounding atmosphere, a detail that helps researchers understand the storm's vertical structure and internal dynamics, building on more than a century of visible light observation of the same feature. The narrow, extremely fast jet stream discovered above the equator gives atmospheric scientists a brand new data point for modeling how energy and momentum move through a gas giant's upper atmosphere, insight that ultimately helps refine climate and circulation models applied to giant exoplanets that can never be imaged this closely. The auroras, both the general polar glow and the specific footprint tied to Io's volcanic activity, demonstrate in vivid visual form how a planet's magnetic field can physically connect to the geology of a moon hundreds of thousands of miles away, converting Vulcus, volcanic material, into a visible light show at the opposite end of a planetary system. Even the faint dust ring, rarely noticed in casual photography, offers clues about the small particles shed by Jupiter's inner moons and swept into orbit by the planet's gravity and radiation environment. For anyone building content, education, or discussion around these images, the most responsible, and frankly, the most genuinely engaging approach is to lean into the explained science rather than manufacture confusion where none exists. Audiences respond to real revelations. Learning that a telescope built to see the birth of galaxies also discovered a 300-mile-per-hour wind hiding above Jupiter's clouds is a legitimately remarkable fact that needs no embellishment. Learning that a distant moon's volcanoes are visibly wired into a planet's aurora across 500 million miles of space is inherently dramatic without requiring invented mystery. Learning that a viral image many people believed was cutting-edge NASA photography was actually digital art from an independent astrophotographer is a genuinely useful piece of media literacy, one that protects an audience from misinformation while still delivering the excitement of a good reveal. Presenting Jupiter this way, grounded entirely in verified NASA, ESA, and peer-reviewed research, respects both the audience and the extraordinary engineering achievement that Webb represents, while still delivering the sense of wonder that first drew attention to these images in the first place. Looking ahead, Webb's solar system program is expected to continue delivering results of this caliber for years to come, since the telescope's operational lifetime, originally estimated at 5 to 10 years based on fuel reserves, has already been extended by NASA thanks to a highly precise launch trajectory that conserved more propellant than engineers initially expected, potentially allowing operations to continue for 2 decades or more. Upcoming observatories, including the Nancy Grace Roman Space Telescope, expected to launch in the latter half of this decade, are being designed to complement Webb's infrared vision with wide-field surveys capable of scanning much larger patches of sky at once, which should help identify new targets, including additional giant exoplanets whose atmospheres Webb can then study in the kind of fine detail it has already applied to Jupiter and to distant worlds like WD 1856b. Every new observation adds another data point to an increasingly detailed picture of how gas giants, whether inside our solar system or orbiting stars trillions of miles away, form, evolve, circulate heat and wind through their atmospheres, and interact gravitationally and electromagnetically with the moons and rings that surround them. It also helps to understand exactly how a raw Webb observation becomes the polished, colorful image that eventually reaches the public, because that process is often the source of confusion when people ask why different Jupiter images from Webb can look so different from one another. NIRCam does not capture color the way a phone camera does. It records brightness through a series of narrow filters, each tuned to a specific slice of infrared wavelength, and each of those grayscale filter images is later assigned a color, typically following the convention that shorter wavelengths are rendered as blue and longer wavelengths as red before the layers are combined into a single composite. This is standard practice across essentially all Webb imagery, not just Jupiter, and it is the same basic technique used for decades in professional and amateur astrophotography whenever a telescope observes in wavelengths that fall outside human vision. The scientists and processors who assemble these images, including Judy Schmidt, who has worked on multiple public Webb releases as an experienced image processor collaborating directly with NASA-associated science teams, are not inventing detail or exaggerating features. They are translating real photon counts, calibrated against known reference standards, into a visual form that a human eye can interpret while preserving the underlying scientific accuracy of where light was brighter or dimmer, warmer or cooler, higher or lower in the atmosphere. Understanding this translation step is part of understanding why Webb's Jupiter images can look so radically different from Hubble's without either one being wrong. They are simply recording different physical properties of the same planet using different parts of the electromagnetic spectrum. It is also worth situating Webb's contribution against the long history of Jupiter exploration, because the planet has never lacked attention from spacecraft, even if Webb is the first observatory to study it from so far away with this level of infrared precision. Pioneer 10 and Pioneer 11 made the first flybys in the early 1970s, followed by Voyager 1 and Voyager 2 later that decade, which returned the first truly detailed images of the planet's bands, its great red spot, and its four largest moons, known as the Galilean moons, Io, Europa, Ganymede, and Callisto, named for the astronomer who first observed them through a telescope in 1610. The Galileo spacecraft orbited Jupiter directly from 1995 to 2003, dropping a probe into the planet's atmosphere and returning the first direct in situ measurements of Jovian weather, while the Juno spacecraft, which has been orbiting Jupiter since 2016, has spent years mapping the planet's gravity field, magnetic field, and deep atmospheric structure from remarkably close polar orbits, at times passing within a few thousand miles of the cloud tops. Each of these missions contributed a different piece of the puzzle. Flyby missions gave the first glimpses, orbital missions gave sustained close-up monitoring, and now Webb, despite observing from roughly 400 million miles away rather than from orbit around the planet itself, contributes a wavelength range and a level of atmospheric resolution that none of those earlier missions carried. The jet stream discovery is a direct illustration of that complementary relationship, because it was found in a layer of atmosphere positioned precisely where Webb's particular infrared sensitivity excels, a layer that spacecraft focused on other wavelengths or other altitudes had simply never been able to isolate as clearly. The Great Red Spot itself offers another example of how Webb's data connects to a much longer scientific record rather than existing in isolation. Continuous observation of the storm dates back to at least the late 19th century, and more careful tracking through the 20th and 21st centuries has shown that the storm has been slowly shrinking over time, from an estimated width of roughly 25,000 miles in the late 1800s to something closer to 10,000 miles in recent measurements, still comfortably larger than the diameter of Earth, but a documented long-term change rather than a static, unchanging feature. Webb's infrared imaging adds a new layer to that historical dataset by showing, for the first time with this clarity, how the storm's cloud top altitude compares to the surrounding atmosphere, giving atmospheric scientists another variable to track over the coming years and decades alongside its well-documented shrinking width. Researchers can now, in principle, watch not just how large the Great Red Spot is on any given year, but how high its clouds are punching relative to the atmosphere around it, adding real quantitative depth to a storm that has captured public imagination since long before spaceflight existed at all. None of this scientific richness has required a single fabricated claim, an invented anomaly, or a misattributed image, and that is precisely the point worth carrying into any presentation of this material. Jupiter, as seen through Webb, is not a planet full of mysteries science cannot explain. It is a planet whose real, documented, and increasingly well-understood features happen to be dramatic, enough on their own that no embellishment is needed. A genuinely engaging treatment of this subject does not need to borrow drama from misinformation. It only needs to accurately convey just how much has already been discovered, verified, and explained by the scientists doing the actual work. One more dimension of this story is worth noting before drawing everything together: the role public engagement has played in how these images reach the world. Unlike many space missions, where data is processed almost entirely inside institutional pipelines before a finished product is ever released, several of Webb's most widely shared Jupiter images have come through collaboration between professional planetary scientists and independent, publicly credited image processors working with openly available raw data. NASA and the Space Telescope Science Institute routinely release calibrated Webb data to public archives. And processors like Judy Schmidt have built long-standing, transparent working relationships with the agency's own science teams, producing composites that are then reviewed, credited, and distributed through official channels such as NASA's Astronomy Picture of the Day service and the European Space Agency's Webb Press Office. This openness is a meaningful safeguard against the kind of misinformation described earlier with the McCarthy art piece. Genuine Webb Jupiter images can almost always be traced back to an identifiable science team, an identifiable dataset, and an official NASA or ESA release, while images with vague or untraceable sourcing, especially ones spreading quickly on social media with dramatic captions and no-named scientists attached, deserve a healthy dose of skepticism before being treated as real data. For anyone producing content about these images, checking that traceability is not a minor technicality. It is the difference between accurately representing one of the more remarkable scientific achievements of the decade and unintentionally spreading a hoax dressed up as astronomy. The transparency also extends to how the scientific community talks about what remains unknown, which is a very different thing from what is falsely labeled as unexplained. Researchers openly acknowledge that questions remain about the precise mechanisms driving some of Jupiter's smaller-scale storm behavior, about how energy moves between different atmospheric layers over long timescales, and about how typical or atypical Jupiter's specific jet stream and auroral patterns are compared to gas giants around other stars. Those are legitimate open questions actively being pursued through further Webb observation time, continued Juno data, and ground-based telescope monitoring, and they are worth mentioning precisely because they show what real scientific uncertainty looks like: specific, narrow, and clearly framed by people who understand the data deeply, rather than the vague, sweeping claims of universal bafflement that tend to appear in sensationalized headlines. Genuine open questions in planetary science are not marketing hooks. They are the actual working edge of the field, and they are usually far more interesting once explained clearly than any invented mystery could be. Jupiter, in other words, has become something unexpected in the story of the James Webb Space Telescope. Not a footnote and not a mystery, but a proving ground. It is the closest, brightest, most familiar possible test of whether an instrument built for the deepest reaches of the observable universe could also turn its attention inward and still deliver genuine scientific discovery. It did. It found wind patterns nobody had measured before. It resolved auroral physics with striking clarity. It captured rings, moons, storms, and volcanic footprints in a single frame, and it did so using real, peer-reviewed, transparently documented science, not manufactured drama. That is the version of this story worth telling, because it happens to be both completely true and, on its own merits, one of the more genuinely fascinating results to come out of modern planetary astronomy.